I'm Sara Navarro Arredondo. I'm the ESR 12, and I will present my work on, and also further work that is pending within this project. And well, my work is the characterization of methane flames and acoustically forced and unforced diesel spray flames at elevated pressure and preheated air. And well, the outline of this presentation will be about the research question, the research method that I'm using, the results that I obtained so far, links to other Magister ESR projects, about the dissemination and publications, and also further work that is to do. Before going into my project, let's remember that the Magister project is divided in these 5 work packages, or more, but for the ESR, just these 5s. The ones that we already seen: machine learning, combustion models, acoustic models, and experimental work. That is the work that already Thomas presented before me about the characterization of the spray with acoustic forcing. And for my side, while in the beginning of the project was focused on liquid fuel combustion, the path got changed, and now it's a 2-part experiments. So the question that I have is, what are the characteristics of this high amplitude oscillation in an atmospheric pressure Raike tube combustor? How we can characterize the stable regime from the unstable to the stable to the unstable and its transition, and how we can acknowledge from nonlinear analysis techniques the chaotic nature of thermoacoustic instabilities, and also in acknowledge them, how we can predict them. And the second part is how to proper elements of the liquid fuel combustion can add to this understanding, while talking about a more complex type of combustor, high pressure and high temperature inlet air. So the research method, again, I have this 2 parts project. So for the experiments on the first combustor, the Raike tube type of combustor, is to determine the flame's response to changes in the airflow in the combustion reaction, and to perform this nonlinear analysis that, for my case, was doing 3 first portraits. Whereas for the other combustor, this high pressure, high temperature air, inlet air, diesel spray flame, is to perform maybe the same characterization, but also do the acoustic forcing and determine the flame transfer function. So well, for the combustor that I've been working on is here this picture is a Raike tube type combustor. Some professors maybe are familiar with it because it has starred in other projects, and also another universities have a similar model. It can go from 30 up to 50 or 60 kilowatts. It's at atmospheric pressure and was designed to provide conditions to study combustion-driven thermoacoustic and limit cycle. It gives a technically premixed flame. It has an open-end condition of streams and a closed-end condition of streams and an open-end condition downstreams to the atmosphere. And while we can monitor the pressure, we have 6 pressure transducers, we have a few thermocouples, and also we can have optical access to have the heat release. And while we operate this combustor with methane, here is the burner. There is this triangle with 22 drill holes of 2 millimeters that make for a good mix of the air and the methane. It doesn't allow for shock conditions, and it goes for a Mach number of 0.1 to 0.5, depending on the flow parameters, and low pressure drop. And I have a small video of the stable condition in the combustor, and then when it's unstable and the flame gets more turbulent and looks really nice, very blue. Okay. Okay, so what I have done, and I have presented a bit of this work before in other progress meetings, is that we do these three-phase portraits of a time series given by the pressure transducers. And while this is not a new idea, there are a few very neat papers by Sojet team, and when he does this kind of analysis, and actually it looks pretty well because they're working in the laminar regime, so the differences are very, very clear. And this looks nice, it works, but well, for the laminars, they're working about 1,100 Reynolds number. And here we go from the 7,000 to 15,000 Reynolds numbers. So we are more turbulent, and but still you can see very clearly how it goes from a stable case to an unstable case. And okay, so what we went from the stable case that has bigger airflow to more richer still within the lean regime. Okay, so here are these two cases, and just for a reference for you, the 1.8 is 11,100 Reynolds number, and the 1.2 is 7,000, 1,600. And well, you can see the power spectral density. You can see that it has this peaks in frequency here in about 260, and here a bit lower in 220 hertz. And well, to create these three-phase portraits, we use the coordinates made from this same variable, in our case the pressure signal, and its time delay copies. To define proper delay times of these copies, we obtain the average mutual information function that it relates to measurements that are close enough to have some relationship between them, but are also kind of independent. We also need the lowest integral global dimension, that is the amount of dimensions that are necessary to unfold the observed orbits. Here is that it falls on 3. And from these two numbers, we can generate our three-phase portraits. You can see here that all the trajectories are very collapsing together, entangled. And when we are in the unstable cases, they unfold and they make this torus shape. So we repeat a bit this analysis. We want to make a full trajectory from the leanest case that the combustor can allow without losing the flame to the richest without the system getting too unstable or super hot. And in this way, it was also our intention to see if there is some hysteresis path. And well, they are not totally equivalent. You can see that the idea is that we go from stable to unstable, and from unstable to stable. And when we go this way, the unstable case, the chaotic behavior, it prevails a bit. And this is good to consider when we are thinking on control of these instabilities. It's good to consider. And well, a bit more about these trajectories. You can see again that the attractor unfolds when it goes in the unstable cases, and all the trajectories are going together when it's in the stable. Well, this behavior can be attributed to chaos or might not, so we better verify the existence of chaos. And well, Oshnish already talked about this test for chaos, and while he did not like it, we think it's very nice, very neat way to prove the chaos in our system. This is the TIS-01 proposed initially by Godwald and Melbourne not that long ago. And this test has been used already to check chaotic behavior in combustors, so it's already proved. In another works in non-turbulent systems, it goes very neat from, and you can see very the opposition between the 0 and the 1. In this case, it's for the turbulence, it doesn't get that different, but still you can see that if it tends to 0, the data is not chaotic. If it tends to 1, the data is chaotic. And for the very stable case, it's very, very, very close to 1. So with this methodology, you have an input that is the time series, and the output is a single number, which is 0, 1. It's a regression method that consists on a linear regression of the mean square displacement. And it's very nice. We also evaluate the pressure histograms generated for each case, and you can see here it's from air-fuel equivalence ratio of 1.8, again, high airflow, transitionary state of 1.6, and unstable case of 1.2. And you can see how this pressure distribution opens at the rate of getting closer to the unstable situation. And also we make different presentations of this data with a bifurcation diagram of the pressure values. The figure shows that the lower the air-fuel equivalence values goes, the distribution of the pressure is more scattered. And also we have a new light of what we can observe from the histograms about the pressure distribution, how as we decrease the air-fuel equivalence radio, we have bigger pressure variations with respect to the mean. That's a general idea of what we are observing and the results. And for the links to other Magister ESR projects, the main collaboration will be with Ali. He already told yesterday about how he's doing simulation with this UT burner that I'm about to use. Well, I'm about to use, and he will do simulations, and we will have like the comparison between these and the experiments. Also with Thomas, that present his results before. He already talked that he will do some spray experiments with the burner. He has already that burner, and we will see. He will do conditions equivalent to what are we doing, and it will help us to really understand what's happening with the liquid fuel combustion. And also with Eli J, he already talked yesterday about his impedance model. He passed it to me, he explained it to me. Thank you, Ali, for that. And the idea is that we can test it on the spray experiments. There are from dissemination and publications. I have this conference paper that I present in 2019, and this new article about the results that I show you that is to be submitted. But for me also, it's important that this is not the end. The end of my contract is in May of next year, so I still have 15 months, and there's a lot of to do for me in the liquid fuel experiments. The combustor last year, with all the situation of the pandemic, it got a bit delayed, and even right now the laboratory is kind of a problem to do the process, the progress as it will be before, but it's almost ready, and we will do the diesel spray frame test with this UT burner that Ali talked a bit about, and I will talk a bit also. Variable pressure and high temperature inlet air, and these experiments with acoustic forcing. This is the combustor that also has been used before in another experiments.
You don't have much time anymore, Sara.
Oh God, okay, I'm going faster. So, this is go to 500 kilowatts and 5 bars. It's using diesel as fuel. It has 11 pressure transducer, and it has optical access. And Ali talked about this burner. It was based on the K81, but we had to enlarge it yet because we were using higher airflows, and but also change the entrance angles of the secondary inlet. So we get a coast wheel, and the floor is mature side. It has a good recirculation zone, and it goes for a more compact flame that will be prone to these high amplitude oscillations. And there are plenty further publications totally based on these liquid fuel experiments. And that's all.
Okay, thank you, Sara. Okay, Thomas, can you ask the first question, please?